So for this video, we're going to talk about buoyancy force. And the example I want to set up as we look at buoyancy force is typically the reason why rowboats are made out of wood and not steel, though you can have like some metal canoes and stuff. But you'll probably have noticed, if you're any bit familiar with them, the wood ones are much thicker. The metal ones are very, very thin. So we're going to kind of do a theoretical experiment, as you will, set up to show why, if you did have a steel rowboat, it would need to be very, very thin. So for the case of our comparison, let's use the dimensions of a rowboat, but we're going to kind of approximate it to be a rectangular prism. Like a terrible box, but hopefully you'll get the idea for this. A few things I want to talk about as when we're talking about buoyancy force. You'll note that a rowboat is hollow in the middle. You can sit in it. The buoyancy force equation, FB, is defined as the density of the fluid which you're floating in. For the example of this video, we're going to use fresh water. Fresh water is 1,000 kilograms per meter cubed. That's the number we're going to be working with. The next variable in this equation is the volume that's being submerged. Now, for the case of a rowboat, it's not just the volume of the material, because the material is hollowed out. It's the volume of the whole thing. So that includes the air in the middle and everything. You can think of it as the volume displaced by the water. The water is going to be displaced regardless if the thing is hollow or not. And then the acceleration due to gravity. So that's our buoyancy force equation. I am going to get two volumes here for our calculations, just so we can deal with the masses. But when we're talking about submersion, we're talking about the volume of the big shape, not just the material. But let's put some dimensions on our theoretical rowboat. This will be 3 meters. We'll have the depth be 1 meter and the height be 1 meter. And I'm going to have the material thickness be 10 centimeters, which is 0.1 meter, which is about what you'd expect for a boat, maybe a little bigger. But again, this is kind of theoretical. We're going to compare this, though, for both the boat and steel. So let's say our boat is made out of oak wood. I'm going to do an O there for oak wood. Oak wood's density is approximately 750 kilograms per meter cubed. And the density of steel is approximately 7,850 kilograms per meter cubed. So you can already see big difference. So I want us to, let's go ahead and calculate the hollowed out volume. Load out volume. And what this is going to tell me is it's going to tell me exactly how much material I'm working with. And again, this is not the volume I'm going to take for the buoyancy volume. The volume I'm going to take for the buoyancy volume would be like the filled in volume. So we'll also have a filled in volume. And these are going to be the two volumes we're going to be working with. So hollowed out volume, I'm going to make notes here. For our rectangular prism, we would have a side over here. You'd kind of see it back here. Wouldn't really see it. And a side right here. So we have one side here, one side here. So there'd be two of them. In this case, the width of this would be the 1 meter. The height would be the 1 meter. And the thickness would be the 0.1 meters of the material. So I can write this as it would be the 1 by 0.1, or the thickness of the material times 2, because there's two sides. I'm going to add to that, add to that the front. So this would be the front. There's going to be a bottom down here and a back. Now the front, the bottom, and the back are all of the same dimension, because it's 3 by 1, 3 by 1, 3 by 1, because the height and the thickness are, and the depth are about the same. So in this case, I can add them as, let's get this all in the same color. 3 by 1 by 1. Oh, no, this would be 3 by 1 by 0.1. 0.1. That thickness again, I'm going to highlight this here. It'll come back to us in a minute. This is the thickness. So 0.1, I'll write that somewhere else, but that's essentially the thickness. That'll become important later. But there, again, like I said, are 3 of these. So I'm going to multiply it by 3, and I don't know why I'm writing it down here for the filled-in volume. That should go up there. When I calculate this, I get an overall hollowed out volume of 0.92 meters cubed. That's how much volume the material is taking up. So the filled out volume, though, is like the overall volume amount that the boat is equivalent to, including the air that's going to be in between it. But again, that's going to affect the displaced water, so we want to calculate that. This is the big dimensions. This would be the 3 by 1 by 1. So it's just going to be 3 by 1 by 1, or 3 meters cubed. That's the whole filled in volume, the volume of the boat as a whole. Now, how does this help us? We can use the hollowed out volume to figure out how much mass the wood and steel would represent. So let's do it for the wood. So let's figure out the mass of the wood. We're going to do the mass of the, I'm going to call it the oak, and using our density equation. So I'm going to write that down here. Let's do this in a different color. So the density of an object we know is defined as the mass divided by its volume, which means the mass of the object is going to be its density times its volume. Well, the hollowed out volume is the amount of volume the material makes up. So that's how we're going to be able to calculate this. So the mass of the oak wood is going to equal the density of the oak wood times the hollowed out volume. We'll call this volume H for hollowed out. That's just the volume of the material. This is going to be 750 kilograms per meter cubed times 0.92 meters cubed. My meters cubed cancels. I'm just left with kilograms, which is good. That's what I want. And if I plug this into my calculator, I get 690 kilograms. I can do the same thing for the steel. So the mass of the steel would be the density of the steel times the hollowed out volume. Again, if I kept it at the same thickness, it would theoretically take up the same material space. So this would be 7,850 kilograms per meter cubed times 0.92 meters cubed, which would equal 7,220 kilograms. So quite a bit more material we're using for that. Hence, you can probably see that there's going to be something we could do maybe to make the material lighter, so to speak, is by making the sides thinner, which you can do with metal. It has a higher stress tensor, but that's a different topic. So let's go ahead and let's figure out what the buoyancy force required to keep the wooden boat afloat would be without passengers. All right, so we're going to calculate it with passengers later, but let's assume it's empty for the moment. So the buoyancy force, if the boat is going to stay stationary, let's think about its free body diagram. The boat's just going to be sitting there on the water. The thing pulling it down is gravity. The thing keeping it up is, oh, goodness, let's draw that straight, please, is the buoyancy force. And those should be equal and opposite if the boat's going to float there. So this is going to equal the gravitational force. So the buoyancy force, as defined as the density of the fluid or the material that it's on. In this case, this is the water, W for water, not wood. That's the 1,000 kilograms. The volume that's being submerged, I'm going to write an S here to denote this is the submerged volume, not the hollowed out volume. This is going to compare to the full volume of the boat. We want that to compare to it, right? Because if the whole volume of the boat is, if the submerged volume is greater than the whole volume of the boat, then the boat's going to sink. So that's the submerged volume, and then gravity. That needs to equal the mass of the boat, which in this case, for this specific example, is going to be the mass of the oak wood boat times gravity. So you'll notice my gravity terms both cancel, and I get this relationship for density, volume submerged, and mass of the oak wood, which is comparative to the density formula. I want to be very careful, though. This isn't just the density formula for oak wood. It's actually what this is doing is it's comparing densities of the boat's material to the density of the fluid it's in. Things that have lighter densities float on top of things that have, things that have smaller densities float on top of things that have bigger densities. And this is actually what that's doing, is comparing them, which is why all the variables are the same, but you've got to be careful of the subscripts here. But I'm going to set this equal to submerged volume, and we're going to play around with it a little bit. So the submerged volume, in this case, I'm just going to divide the density of the water the other side, which I'm just going to write out because it's a constant. The density of the water is not going to change. This is going to be the mass of the oak wood boat divided by water's density, which is 1,000 kilograms per meter cubed. And we're going to actually calculate, if I have a boat with this dimension made out of oak wood, we know how much mass what the mass is going to be because we know how much space it's occupying. We can actually calculate that. We just calculated its mass, so let's go ahead and plug that in. I get 690 kilograms divided by 1,000 kilograms per meter cubed. Move this over here. We don't run out of space. There's going to be so many things. This is going to equal 0.69 meters cubed. That's how much the submerged volume is for this wooden boat, this wooden rowboat, without people in it, right? So let's take into account that's without people. But if the overall boat volume is 3 meters, and I calculate that, 0.67 is only about 23% of 3 meters. So it's sitting real nice. It's got some extra space. I can also compare this to, I want to actually be able to add people. How many people could we add before this thing starts to sink, right? The idea is that the submerged volume needs to be less than the overall volume of the boat. So my submerged volume should be less than 3 meters cubed. And let's assume the average mass of a person. So a person's average mass, we'll do person mass or mass of person, whatever we want to call that, is 70 kilograms. Okay. I can kind of set up the equation like this. I can say, well, my submerged volume, if it has to be less than 3 meters cubed, this is going to just be an inequality, has to be the mass of the Oakwood boat, which we know 690 kilograms, plus the mass of our passengers, we'll call P. We'll call it their collective mass, which we'll calculate in a second, divided by the density of the water. And this better be less than 3 meters cubed. We already know the mass of the boat itself just comes out to 0.69. So we should probably think we have some wiggle room here, which we do. If it's an inequality, I can treat it just like an equation in terms of what I do for algebra. The only thing that is different with an inequality is you flip the sign if I multiply or divide by negative. But I'm not going to be doing that here, so things just stay the way it would be if it were an equal sign. I'm going to multiply the 1,000 to the other side, so I get 690 kilograms plus the collective mass of the passengers to be less than 3,000, and I get kilograms as a unit there. I'm going to subtract the 690, so I get the passengers collectively need to be less than 2,310 kilograms. If I divide that by 70 kilograms a person, give or take, again, this is theoretical, I can fit approximately 33 people before this, pretend that's spelled correctly, before this starts to sink, right? So wooden rowboat, pretty useful, right? Is this very realistic? Could you even logically fit 33 people in here? No. So you could probably stack a cooler, hang out with some friends on the rowboat. It's not really going to sink. Now let's compare this with the steel rowboat. Now, the steel rowboat, so we're going to use the same density buoyancy force equation. The buoyancy force has to equal the gravitational force. So the density of the water, the volume submerged, and gravity has to equal the mass of the material of the boat, which in this case is steel, and gravity. Gravity cancels again. I get this relationship for volume submerged as equal to the mass of the steel boat divided by the density of the water, which again, the density of water is just constant 1,000 at this point, kilograms per meter cubed. You can already see we're gonna have a problem with this. The mass of the steel boat, if it's the same thickness as the wooden boat, is 7,220 kilograms divided by the 1,000 kilograms per meter cubed. I get about 7.2 kilograms, or not kilograms, sorry, meters cubed. as my volume submerged. That's over twice the volume that the boat actually occupies. The boat's only 3 meters cubed. So it's going to sink, and it's going to sink fast, right? So it's very dense. Now, can you make a rowboat out of steel? Yes. How do they do it? They make it thinner. You'll like never see a steel rowboat that's 10 centimeters thick, usually on scales of millimeters. But given our current theoretical situation, let's actually calculate how thick could I make this steel rowboat to keep it afloat. First thing I'm going to do is I'm going to write my hollowed out volume with respect to general terms. You'll remember I highlighted the thickness in both scenarios. I'm going to replace that because that's the thing I want to change. I want to keep the dimensions of the boat 3 meters by 1 meter by 1 meter. I just want to make the material thinner. So the hollowed out volume, VH, is still going to equal the 1 by 1, but I'm going to call this now by T for thickness. And there's still two sides, so that's still times 2. I'm going to still add to this the 3 by 1, but now it's going to be by T for thickness. And there's still 3, forward, bottom, back. Then that gives me a cumulative total of 11 times the thickness in meters cubed for my volume that I'm going to be working with. So this is the amount of volume of the steel boat that I could be working with. And then let's remember, how did we calculate the mass of the steel boat with respect to the volume? The mass of the steel boat was equal to the density of the steel times the hollowed out volume. So that was the volume of the material, which in this case, it's the mass of the steel, and this is our new hollowed out volume. That's what we just calculated. So I'm going to call this 11 times the thickness in meters cubed. Okay, that's my relationship for what my new mass of the steel is going to be. Because it's going to be lighter. There's going to be less steel if I thin it out, if I make it thinner. That should hopefully register. So our mass is going to change. We're just writing it as a function of how thick it is. I'm going to plug this into my buoyancy force equation. Now, if I want it to stay afloat, I'm going to use this submerged volume that we've been dealing with here, this submerged volume relationship. So this volume submerged needs to still be less than our 3 meters cubed because we haven't changed the overall dimensions of the boat. We're just making the material thinner. So the submerged volume still needs to be less than 3 meters cubed. I'm going to plug this in, though, for my submerged volume. I know it's the mass of the material, the mass of the steel. So this means that it's the mass of the steel divided by the 1,000 kilograms per meter cubed. That is the density of the water. This needs to be less than 3 meters cubed. Well, I have this new equation for mass of the steel. That's going to be the density of the steel times 11T. That has to do with the hollowed out volume and the thickness in meters cubed, divided by the mass of the water, which is 1,000 kilograms per meter cubed. That has to be less than 3 meters cubed. I'm so running out of space, but we're going to calculate it up here. The density of the steel is the same because it's steel, 7,850 kilograms per meter cubed. This is divided by the 1,000 kilograms per meter cubed of water times 11T meters cubed. It has to be less than 3 meters cubed. And I'm going to solve for T. When I do this, I multiply, divide again. It's an inequality, but I'm not multiplying or dividing by negative, so it's just like it would be an equation. The thickness needs to be less than 3.5 centimeters, or when I calculate it, done. So I can, it's a little more than half the initial thickness because it was 10 centimeters. If I drop, and I probably want to cut it down before because this isn't even filling it with people. This is just to keep the boat itself from its own mass floating. But if I make the thinness of the steel, or if I make the steel material thinner, I can get a steel boat to float. And you've probably been aware there are big battleships that float, but again, the material is tends to be a lot thinner than wood. Both, I do want to point out both these calculations assume that there's an open top, right? You can have submarines that have closed tops that also deal with buoyancy force. In fact, actually, how some submarines can sink and float is by changing their buoyancy levels. There's like you can think of the walls have a inner plate, two plates, right, where they can fill it with water and make their mass, that hollowed out mass change in terms of changing their buoyancy.